As we get closer to doing statistical inference in STAT 2.3x, one of the quantities we need to start looking at is the sample average. We're going to be having a lot to do with sample averages, special cases of which are sample proportions of people who will vote a certain way, proportion of people who have incomes in a certain range, the simple average itself, the average rent paid by a community, and so on, may be quantities that are going to be of interest. And so we're going to take a look at moving from the sample sum to the sample average. Now, you've done this before in back in section 3 actually, and so here is what we saw then. You have a number of draws with replacement from a box, and you are looking now at the average of the numbers that you have drawn, which is of course the sum of the numbers that you have drawn divided by the number of draws. And what we worked out with a little calculation is that what you expect to get as the sample average is the average that you started with. And in the special case of zeros and ones, where your list of numbers in your box is a proportion p of ones and 1 minus p of zeros, the sum of the numbers that you draw is the sum of zeros and ones, and so it is the number of successes that you are drawing. And therefore the average of the numbers that you draw is the sum, that is the number of successes that you've got, divided by the number of draws. And so it's the proportion of successes. And that is a crucial observation. It's been made before, and I'm making it again. The average of a list of zeros and ones is the proportion of ones in it. And by exactly the same calculation that we saw previously, the expected proportion of ones in the sample, that is the expected proportion of successes that you get, is equal to the proportion of successes in your original population. Now, both of these are expected values, expected proportions, expected sample averages, and you know from STAT 2.1 and elsewhere that an expectation is all well and good, but it's only really useful once you have a margin of error attached to it. And so let's go ahead and crank that out now. So we're going to look at the accuracy of a sample average, and I want to define this word population, because it's natural to think of it as a set of people, but I am not thinking of it as a set of people. I'm thinking of it as a set of numbers. And if you would like, you can imagine a set of people behind those numbers. So, for example, everybody in a city, and each person is holding a ticket, and on the ticket is that person's age. Then the population is the list of ages. For now, whether the population is big or small is not going to matter. You can imagine it however you wish. For me, at the moment, it is just a list of numbers. And what I have here is a set of n draws with replacement from this list. And I'm going to call the average of this list mu, that's the Greek m for mean, and the SD of this list sigma, that's the Greek S. And there is, once you've done this, you have n numbers, each of which comes from this list, and there is one operation on those n numbers that you understand very well, and that's adding them up. So if you take the sample sum, that is the sum of these guys, then you have the expected sample sum is the number of draws times the average of the box. The standard error for the sample sum is square root of the number of draws times the SD of the box. Nothing new there. And by the central limit theorem, if the number of draws is large, then the probability distribution of the sample sum is roughly normal. So we are changing variables now to the sample mean. How do you get the sample mean? You take the sample sum and you divide by the number of elements in the sample. So what's the expected value of the sample mean? That's the expected value of the sample sum divided by the sample size. So the expected value of the sample sum is n mu. Divide that by n and you've just got mu. Nothing new here. We did it a couple of slides ago. What you can now do is put a margin of error on this expectation that you have. The standard error for the sample mean is the standard error for the sample sum divided by the sample size. So what's the standard error for the sample sum? Well, you know what it is. It is root n sigma. So root n sigma divided by n. And you know, you would love to just cancel these n's. But you can't because this one has a square root and this one doesn't. That's fine. We'll write the denominator as the square root of n times the square root of n, and then we are allowed to cancel one of these. And so what we are left with is the SD of your list in the numerator and square root of n now in the denominator. And since the distribution of the sample sum was bell-shaped, the sample mean is just that with a constant multiplier, so the distribution of that will be bell-shaped as well. Provided, of course, the sample size is large. Now what I'd like to do is I'd like to take a look at this expected sample average and the standard error and note a couple of things. We have noted before in section 3 that the expected sample average is the population average regardless of the number of draws. There is no n in this answer. There is, of course, in the standard error an n in the answer, and where is that n? It's in the denominator. And that is telling you that as the sample gets larger, that is as n gets larger, the standard error for the sample mean gets smaller. In other words, you get better and better and better at predicting the sample mean as you increase the sample size. And that's going to be a useful observation for the future. We will come back to that in much greater detail, but for now note, as the sample size increases, the sample mean gets less variable, the sample sum gets more variable. Quick example, this is a data set that you have seen before. It's the weight of a random sample of 100 people, and we're assuming that that's like drawing 100 times with replacement from a list that has an average of 170 and an SD of 15, and these are all weights in pounds. And so if I ask you now, what is the chance that in the sample, among these sampled people, the average weight is between 169 and 171? What have I just asked you? Well, the population average is 170, and I'm asking you, what's the chance that the sample average is at most 1 pound away from that? 1 pound is not a lot of pounds. So let's see what this chance is. And the thing to do in such a situation is to say, all right, this is talking about a random variable, which is the average weight of the sampled people. Let me forget the question and just think about what I expect that average weight to be. So what I expect that average weight in the sample to be is the same as the average that I saw in the population. That's one of the things we just wrote down. And so you quickly have the expected value of the sample average is 170 pounds. This is an expected value. It's got a plus or minus number on it, and that is the SE for the sample average, for which we now have a formula. The standard error of the sample average is take the SD of your population, divide by the square root of the number of draws. So what you got? 15 divided by 10. That's 1.5 pounds. That's pretty small. You're guessing 170 pounds, give or take 1.5 pounds. So you may be off by 1.5, you may be off by 3, you may be off by 4.5 if you're really unlucky, but you really don't expect to be off by much more than that. And we're not going that far. We're only allowing ourselves to go 1 pound in either direction. So what is the thing to do now? Well, the thing to do now is to say, all right, well, I expect the sample average to have a probability distribution that follows the normal curve centered at 170, give or take 1.5. I want the chance of getting between 169 and 171. And so what do? Well, I convert these two to standard units. And I've just done that. Please note, there are no 0.5s. There is no continuity correction here, for two reasons. One is that the weights don't have to be in full pounds. And the second is averages, because of that denominator, don't have to be integers at all, even if the original list was. And so not correcting is perfectly justified here. So what we have is the first endpoint in standard units is minus 2/3 and the second one is plus 2/3, and you want the area between those two numbers under the standard normal curve. So you go to your applet and it says that the chance is just under a half. And so if you go back to the question again, we asked, what is the chance that in the sample the average is within 1 pound of the average in the population? That chance is substantial. It's almost a half. And that is because you are pretty sharp at predicting averages. Now, an important special case of this technique is the situation where you have zeros and ones in your population. So you have n rows at random with replacement from this box of zeros and ones, and you know very well that the average of this box is the average of a 0-1 box indeed is the proportion of ones in it, and the SD of this box is the SD of a list of zeros and ones is square root fraction of ones times fraction of zeros. So your population mean is P and the population SD is root P1 minus P. This is what I was calling mu in the general case, and this is what I was calling sigma. In the case of zeros and ones, you can simply work both of them out from the proportion of ones. So now what? What you understand really well is what happens when you add these n zeros and ones that you've drawn, because then you get the number of successes, and that you know very well. The sample sum has the binomial distribution. Its expected value is NP. Its standard error is the square root of n times p times 1 minus p. And you know that when n is large, the binomial distribution is roughly normal. So you understand the sum very well. And now on to the average, which when you average zeros and ones, you get the proportion of ones. Alright, so what its mean, its expected value is P, that is the population mean, and the standard error is take the SD of the population and divide by the square root of the sample size. So that's square root P times 1 minus P divided by square root of n. And by properties of square roots, you can just take the division first and then do the square root once and for all over the whole lot. So root P1 minus P divided by n is the standard error for the sample proportion. Once again, the n is in the denominator, and so the sample proportion standard error goes down as you increase sample size. And as before, if your sample size is large, then the probability distribution of this sample proportion is roughly normal. So how does this affect us in calculations? Well, let's take a look at something we said before in the law of large numbers. I'm going to look at 1,000 tosses of a coin, and I'm going to look to see what proportion of heads I get. No surprise, I expect to get half heads. And now I can put a plus or minus on it with a standard error of square root fraction of ones times fraction of zeros divided by the sample size. And that's about 1.6%. And so in words, what I've said is, if I toss a coin 1,000 times, I expect 50% heads. Give or take about 1.6%, say about 1.5% is what I expect. So 48.5 to 49.5, roughly, maybe one more standard error on either side. Not much more than that. 3 at the most, maybe. Alright, so that's for 1,000. What happens if you take 10,000? Play the same game again, and now you have a much smaller standard error for the proportion. For 10,000 tosses, you're saying you expect the same 50% heads, but now your margin of error is 0.5%, not 1.5%. And that's exactly what the law of averages was saying. It was saying that as you increase the number of tosses, then the sample proportion of heads that you get gets closer and closer to the theoretical probability of a half. And now you have numbers to put on that tends to get closer and closer. You actually have a standard error that you've calculated, and you can see that the one with the bigger number of trials is just smaller. Now, while we're on the subject of comparisons, let's do another comparison that's revealing. And so I will start by a recap of what we just did. 10,000 tosses of a coin, the expected proportion of heads is a half with an SE of square root of fraction of ones times fraction of zeros divided by sample size, and I have an answer here. So previously I was varying the number of tosses. I'm now going to vary the coin. This coin is just an ordinary coin. It's fair. What happens if you take a biased coin here? Well, let's look at one biased coin that is a call to a random number generator, and you look at getting a 0 as a success, then the chance of getting a 0 is 1/10. And so in 10,000 calls to this generator, the expected proportion of zeros is 1/10 with a standard error of square root fraction of ones times fraction of zeros divided by sample size. And that's 0.003, that's 0.3 of 1%, and it's smaller than what we got for the fair coin. So what happened here? We started with the fair coin, and then we varied the coin. We said, okay, we'll take a biased coin, and for this particular biased coin, our standard error is smaller than it was when the coin was fair and the same number of tosses. So what would happen if we used a different bias here? Well, we can just plot the function square root of p times 1 minus p. P is a proportion, it's between 0 and 1, and what's being plotted here is the square root of p times 1 minus p, like that. And at a half, you see that it's at its peak of a half, and at p equals 1/2, what's root p times 1 minus p? It's root of 0.5 times 0.5, which is 0.5. No surprise there. That is a correct graph. And you can see that this graph has its maximum at a half. And so if you have 10,000 tosses of a coin, any coin, the biggest possible standard error that you're going to get is when the coin is fair. Any other coin is somehow easier to predict, and it will give you a smaller standard error. And this is worth noting for the future when we're doing statistics and we don't actually know the population that we're drawing from. It is useful to know that if the population has zeros and ones, then it is most variable when it has half zeros and half ones. The fair coin is the most variable among all coins. Oh, by the way, this is of course done using a computer to graph a function. The fact that this function square root p times 1 minus p has its maximum at p equals a half really is possible to see just in words. P times 1 minus p is p minus p squared, and that as a function of p is a parabola. And it's a parabola that's sort of pointing downwards, as it were, because there's minus p squared. And where is it 0? Well, it's a 0 at 0 and at 1, and so its peak must be exactly in the middle of 0 and 1. This function is symmetric about 0 and 1, so not at all surprising that its peak is at a half. So we'll put this thought away and come back to it in a lecture or two. What we're going to leave this discussion with is the fact that you get more accurate at predicting averages and percents as you increase the sample size, but that our sampling has been done throughout with replacement. And when you are sampling from populations of people, that's a rather unnatural thing to do. You want to sample without replacement. And there's a little wrinkle that gets attached to everything that we've done when you sample without replacement, and that's the business of the next section.